Good morning. Today we will conclude our course Vehicle Dynamics with the concluding part of our tire mechanics, what we have been doing maybe past 4-5 lectures. And last class we were in the tire mechanics, particularly we have learnt about how do you characterize the properties of tire during cornering using a stretched string model proposed by Temple and Von Schlippe. So what we have done in that is, we have looked at a tire not as a elastic tread band, what was considered in a Julien's model. Instead, Temple and Von Schlippe proposed the tire to be a stretched string model, wherein we define an equatorial line, and that equatorial line deformation for the psi force is what we considered, and its physics is what we looked at. And we have defined forces in that structured string free body diagram for an element chosen from the center of the contact patch at the distance x comma y. So you had at a distance x along the contact patch from in front of the center of the contact patch, a lateral deflection y defined for an element. And that element, if you look at, there are two forces. One is the force due to the lateral stiffness of the tire, that essentially represent your sidewall stiffness, and the one end is connected to the string, other end is connected to the rim, so that you are able to have the force due to this sidewall stiffness, and its elasticity and its deformation is responsible. Another one is the tension in the stretched string, so that tension component. So if you look at the part of the line which is in the contact patch called contact line of equatorial line, we were able to define its front as it enters the contact patch, what is its lateral deflection, as it leaves the contact patch, what is its lateral deflection, y1 and y2. And the free length of the equatorial line is not subjected to these two forces which are in the element, right? So that is what is the basis for us to define deflection y1 and y2, and we looked at that can be expressed as an exponential function. And further we were looking at the elemental force, that is one comes from the tension and the other comes from the sidewall stiffness, and that we integrated from LT by 2 to minus LT by 2 to get your force. And we had elemental moment created at the center of the contact patch, and we integrated the same and got a self-aligning torque. And then we also have considered the tire which is not rolling and it is pulled, what would be the deformation. And these are the three aspects that we consider in order to define two important parameters which were appearing in your expression of Fy and Mz, which were your stiffness of the sidewall and relaxation length. So we concluded our lecture, how can you find these two using the expression of pneumatic trail. So pneumatic trail has become an independent of Ky, and then you are able to have, so we have looked at how can you find out this Ky and Lr is what we have stopped in the last class. I'm going to continue with that today's class, and we are going to look at another model called magic formula model. Though the magic formula model is so much now commercial, many vehicle industries or tire suppliers are using that model to real-time scenario predicting in vehicle dynamic simulation. But we are going to look at the Hans-Pajeka magic formula of its base model, the yearly model, and what are those coefficients involved in that model. That model is again an empirical model. So what do you mean by that? We do not have physics or some way of deriving it like we did in Temple's and Von Schlippe model for Fy or Mz, or Julien's model for your tractive force or braking effort. This model essentially would have, empirical data fit, measurement data would be fit appropriately, and the fit would be represented by an equation, and that equation is one single equation which could be used for representing your variation of lateral force as function of slip angle or self-aligning torque as function of slip angle or braking effort as function of skid. So this is essentially is what today's class we are going to look at it. Additionally, we are going to look at in case of cornering, we also do braking, what would be the scenario. So with that, I am going to stop concluding this tire mechanics part of the course. So for that, let me share my presentation. Hope you are able to see this presentation. See, this was that in the last lecture that we have seen. I just quickly browse through them. We also look at the effect of camber angle in lateral force generation. And this is the Temple and Wanshipy model, what I was just briefing in a while. This is what is there here. And finally, we were able to have this relationship of Fy by alpha, Fz by alpha. And this ratios gives you TP, which is pneumatic trail, which is independent of Ky, so which would be sufficient to find out what is LR. And then the other ratio, which is Fy by Fy naught. Fy naught is the lateral force when tire is not rolling. So this 49 and the equation 46 ratio gives you to find out the value of Ky. So this is exactly where we have stopped our last class lecture. What is very important that you should note in our discussion so far is whether if we are revisiting the part what we have learned from Julian's model, or we are revisiting this Temple and Wanshipy model. If you look at, they are purely independent models. So what I mean by purely independent model, the Julian's model do not account the slip angle. It is pure longitudinal slip. And we have studied the physics behind the model, tread band model, which is an elastic model. And for that model, we were deriving an expression of longitudinal tractive force versus slip or braking effort versus skid. That is purely longitudinal model. And if you look at this Wanshipy and Temple model, it is purely a lateral dynamics model, tire lateral dynamics model, wherein we do not consider tractive or braking effort. You do not see in this equation either slip angle, either longitudinal slip or skid. You could see implicitly the dependency of slip angle over here, wherein we defined our slip angle as this, so that we were able to get the expression of Fy and Mz without explicitly appearing it is function of slip angle. So that is another difference of this model when you look at your Julian's model for longitudinal dynamics, wherein you could see that your Fx is a function of I, or braking effort is function of Is explicitly. But now here this model, string model, gives you the expression, but that expression is not explicitly showing Fy is function of alpha, slip angle. So this is the main another difference. So first difference is they are independent model. When one model does not consider slip angle, other model does not consider longitudinal slip or skid, and we have derived this. So what do you mean by that? When you look at your string model, it is the model which is pure cornering. There is no braking or traction during cornering. That is what does these equations 46, 47, 48 and all you should understand. So now we will continue with our understanding of these two models further and go to magic formula model. So for that I have prepared lecture number 45, that is the summary of tire models, what we have seen, and what is this magic formula model, right? So look at that, we started understanding behavior of tire under loaded condition and rolling condition when there is a driving torque MW. This is the driving torque when it is applied, or when it is applied with the braking torque. So how is it behaving? When you apply a driving torque, you see front of the contact patch is under compression. So the elemental length L consider will have its length reduced. So 2 pi r will have reduction in its length. So that is given by this longitudinal strain. So this strain is essentially because of elastic deformation of your tread in front of the contact patch. This undergo compression. This is when you apply the driving torque. And you see this normal distribution, the normal pressure distribution, not normal distribution, normal pressure distribution does not appear to be a normal distribution. Rather, it is skewed to the front of the contact patch, center of the contact patch. And that is what is responsible for your rolling resistance force. But that is not explicitly explained here. And you see this effects, which is longitudinal stress, when it is completely adhered to the contact, you have zero value. As it is gradually increasing, what does that mean? And when it is started sliding from the rear of the contact patch, you would see that you would have the maximum stress value, which would correspond to your maximum tractive force or tractive effort that would be possible. The same free body diagram for your tire under braking, if you look at, instead of the front of the contact patch under compression, it would be under stretch. So the equivalent translational distance of your center of the tire would be more than that of 2 pi r. And you have similarly normal pressure variation as well as the longitudinal stress. So here it is a negative value because it's a braking force that comes. So this two diagram essentially required for you to define what is I, longitudinal slip. So longitudinal slip is R omega minus V by R omega into 100%, or to define skid, which is V minus R omega by V into 100. Right? Why V minus R omega? V would be greater than R omega, where V is given by, in both the case, by effective radius times omega. So this effective radius is different in both the cases. So when it is stretched, you will see this effective radius is greater. When it is under compression, the effective radius here in this RE times omega is different. So you have this definition. Also, we looked at the relationship between IS and I. So I modulus value can be represented IS by 1 minus IS. So this helped us to get, after our Julien's model derivation, what is its equation correspondence for braking effort and skid. So this is what it should come in your mind when you talk about behavior of the tire. So there was a question raised in between during our lecture hours some month ago, that why this point is in front of the contact patch, not here. That is because of the rolling resistance property of your tire, the rolling resistance force that is generated in the tire. Because the tire, though we consider to be an elastic model in a mathematical model, it is really a viscoelastic model. So there is a hysteresis. So when you apply driving torque, it is under compression. When you are reducing the torque or you are not applying torque, it is coming back. So that loading and unloading cycle would have some loss called a hysteresis loss, which is primarily depends upon the tire material and the tire design. That is the reason why your distribution of normal pressure is always, whether it is in the case of application of driving torque or braking torque, would be in front of center of the contact patch. And this would create additionally a moment called rolling resistance moment, and that is what is responsible for rolling resistance force. So keep that in mind, right? So this is helping us to define an important phenomena called the slip and skid. And here we have considered the tire is constrained to go only in straight line. There is no side force acting. That's why it is pure longitudinal dynamics tire model. So that is what we have obtained. So I have put these two equations here, which is summary of your Julien's model, simplified Julien's model, where lambda is not accounted. You know what is lambda? You revisit the lecture in case you do not understand. So this is a simplified model. So till this IC, critical slip value, your model is linear model. And but you get your tractive effort only 50% of what you could get if complete tire that could develop. So this value is corresponding to MEP times W peak value, but you get here only half the value of that. That is why you require the slip to progress further, but it should not go beyond certain value corresponding to this B value, where you get to your maximum value of tractive force. That is where the traction control system play a vital role, like analogous to anti-lock brake system that you have seen. So it would consider that your tire will not completely slide. So there is a portion of the contact patch which should slide, which should slip. So the sliding is required to bring in this non-linearity, but that should not be progress and complete your contact patch till the front of the contact patch. If it comes to this point and the smaller increment in I also would make your tire to fall to a sliding value of your road coefficient. So that is what is important point here. And you see that this equation here is bringing in what is called the CI is longitudinal slip stiffness. This is called a longitudinal slip stiffness, where I is slip, and your Fx, which is addition of the force generated in the sliding zone as well as in an adhesion zone, and it is function of MEP, W, CI, and I. So this is that expression which is going to account even this portion B to A to B nonlinearity. So this is what we have derived in our earlier classes, simplified Julien's model. If you have understood that, you could also use this relation what I have explained you on this IS. I is equal to IS by 1 minus IS, and if you are substituting for that I value, and the CI value can be changed to be skid stiffness. This is called skid stiffness. So your skid stiffness would replace this. So you would get your braking effort consideration would be this. So this is your model, right? So like that you can differentiate your longitudinal and braking force. It's a pure longitudinal tire model. There is no side force or slip angle in this model. And you see this graph I have purposely put. If you look at this braking effort, similarly tractive effort also could be depend on W. I could take this result available in our textbook 1 for you to remember that it is function of load as well. So as the load increases, you see that your tractive force or braking effort in your vehicle also would increase, and the variation is like that. So similarly, you also have operating condition. These two are depending on which is speed. So in such cases, you'll have a linear region, the same stiffness, whereas you will see this kind of plot varying as function of speed as well. As the speed increases, you would see that peak will be increasing, but the slope here appearing different. That means as the load increases, your longitudinal slip stiffness is increases, or skid stiffness is increases, and that is also responsible for your increase in your peak brake force that is available additional to the load. So the load and stiffness would increase, right? So that is what you should understand from this two plot. And again, let us look at why do I say this is so that we will now analogous way look at pure cornering. And this is what we have done in the last class, structure string model. And this string is an equatorial line part which is in contact patch BC, and we define this alpha with the slip angle here, and this contact patch length, the element at the distance X and Y, this point all. So finally we were able to have our Fy expression and MZ expression, wherein you see they are depending on two important parameters. One is Ky, stiffness of the sidewall, another one is Lr, relaxation length. So this determination of them is very tedious process. That is where the experiments were recommended, wherein you are able to get your experiment through experiment your side force per unit slip angle and self-aligning torque per unit slip angle. So having this expression, additionally having expression of Fy where tire is not rolling, These three equations could be used to get defined. One is the pneumatic trade, where in this expression you see there is ky disappeared. So you can get TP experimentally from these two, knowing the TP of your tire, and you would be able to get relaxation length. And similarly, you would be able to get your see Fi naught. So this Fi by Fi naught. So this Fi we will call it as Fi naught. So Fi by Fi naught square would give you this LR disappears and it would be Ky. That's what we have seen in the last class. I missed to put that equation here. Right, so we would appreciate the model proposed by Temple and Wanshipy, which is an analytical model. You would say till this point, but since you are going to use your experimental data and you are going to calculate Ky and LR, it is sometimes called semi-empirical formula, right? Because fully empirical formula is complete fit of your experimental data, and that best fit you express through an equation, that is an empirical formula and its corresponding curve. Semi-empirical formula, you have your basic physics behind the model, like string model or elastic band model, and then you do derive your expression for the efforts, your tractive or braking effort or self-aligning torque like this, and then you call that model as analytical model. So when you have a combination, then it is semi-empirical model. So what is the limitation of Julian's model and Temple and Wanshipy model that we have seen is essentially they are independent model. They do not account your dependency of both slip and slip angle, right? Or skid and slip angle. When skid and slip angle will come when I do cornering and I apply brake. So there will be braking force as well as the side force. So side force is because of the physical phenomena, slip angle, and braking effort is because of phenomena called skid. So the dependency of the resultant force of your longitudinal force and the side force depends on both slip angle and longitudinal and skid. So how do you account such model is what is a very complicated model. We will just see that in a while. I'm not going to derive, but I'm going to give you the formula and then explain you how that accounts both. So for that reason, we can look at now the cornering force and slip angle. So this is a very popular diagram which we have already seen many times in our class hours. And this is a variation of cornering force and slip angle. Like you looked at tractive effort and slip, you have this. So here it is drawn and the value of peak value is limited by the road adhesion coefficient. After that, what would happen is this will go and then fall onto the sliding. That portion is not shown because you are not drawn with the slip angle beyond 16 degrees. If I increase this beyond 16 degrees, this graph will fall down to the sliding. So what do you mean by that? The elastic deformation is the fundamental reason for your force generation, and that elastic deformation and adhesion and sliding phenomena, the contact patch is also very important. So the sliding is happening as it reaches its peak value, as it reaches or it goes beyond the critical, beyond the maximum, beyond the IM or this 16 degree slip angle in this case. Right, so this model again, this plot what is drawn is in absence of I, when I is 0 in your tire. That means it's only by the side force and we are drawing it. So this entire push on the wheel, tire wheel, and the contact patch is expected to generate a Fi alpha in absence of I. So this is pure cornering model. There is no traction or braking. And your variation for a radial tire and bias ply tire that we have seen. And the slope at this line drawn tangent to this point is what is C alpha. So this C alpha can be considered to be constant, but if you look at in reality, it is not constant, as this force generation depends upon load and operating condition of your vehicle. you would see this alpha, C alpha can be represented as a quadratic function of Fy, which you have used in our suspension roll in roll of your vehicle, if you recollect your lecture. So that is what is the C alpha, cornering stiffness. So what you can do in the Julien's model, how it is proposed, the same approach one can have, and you can derive your expression for pure side force like that. So the Cs is replaced by C alpha and I is replaced by tan alpha. The small angle of alpha, this is alpha itself. So this is an analogous equation for side force, which I am not deriving, but one could easily understand how this equation comes if you have understood the derivation of simplified Julien's model, what we have looked at. So this Fi alpha and Fx, what we have derived, can be combined again with the characteristic length definition, all we have looked at in our Julien's model with a similar approach, and you would be able to have your expression. So now let me just explain before going to that the effect of tractive and braking effort on these cornering characteristics. So we looked at them independently. Now we are going to look at their effect on cornering. That means what? Look at these two plots are there on the slide. One is for bias ply, another one is for radial ply tire. Let us look at now this radial ply tire model. So you see on a horizontal axis there is driving, there is braking. So the force here Newton given is driving means tractive effort, and on this side it's braking effort. You know they are in opposite direction acting in the contact patch. So now you see this vertical axis is representing your side force, that is lateral force developed. When what is this point 0? This is neither driving condition or braking condition. That's only pure free rolling condition of your tire, and you would get a maximum value of your maximum value that is possible for you to get is this value Fy. At that time there is no tractive force. If tractive force comes, what will happen? This Fy value start decreasing, and it is limited by this value here. So this is limited by this value means this mu value. So beyond that it is going to be falling on mu s value. So this mu value given here would fall to mu s value beyond this, or it touches this point. So this mu s value is what it refers to. Mu value given here is the road surface characteristics, right? And this entire thing is for the rated pressure and the load condition for this particular speed on this tire of 165 mm width and 15-inch rim tire, radial ply tire, that you look at it. So if you are applying braking, that means what? You are doing hard cornering and you apply braking, then you will have your braking force also coming into picture, addition to this Fy. So that would be somewhere here correspondingly. So if you look at that, this is what is your resultant. This resultant would go and touch this value here at one point. So this as it moves here. So you see that it is going to be a very small Fy here, and you have a braking. When it touches this, it is coming to this maximum possible lateral force as well as the longitudinal force given. So the maximum possible resultant force. The moment it touches the circle, that means the tire would slip in arbitrary direction. We cannot predict what direction the tire is going to skid or slide on the road. So it is not advisable there. So what would happen? The moment it touches that and it is indicating that sliding can happen. So your requirement of your slip angle for any given traction. So if this is my requirement and if I apply braking, I cannot achieve that requirement here. So I have to get that by having an increase in slip angle. So that is what is manifesting and that is the good behavior of your pneumatic tire. Automatically your slip angle will increase. Though there is braking effort appearing here, this component, you would also have your requirement of your Fy is obtained by getting slip angle increases. So that is what you understand from this diagram. So now the combined cornering and braking, if you have to look at, that is resultant of your both the forces, and the resultant force has got its limitation given by this peripheral circle, this two concentric circles for different value of mu. It should not touch that. right? And you see it is as your braking force increases, your lateral force decreases. But I require that then my tire has to slip. So what is that is happening? Why there is a decrease in lateral force is because of mobilization of the adhesion zone which is available in the contact patch is being shared by your braking force. So it is all the adhesion of the contact patch. If entire contact patch is adhered, I would be limited with 50% of my available MEP times W. But I should go beyond it. That is what is going beyond critical skid or critical slip angle. So when I go beyond that, I would be able to extract my maximum value. I would be able to work at the vicinity of this circle, vicinity of these circles. So for that purpose, I should see such model where it is able to give you an framework for to have an analytical formula. This framework is what is called the friction ellipse concept, very popular, and that's what we would see in a while. So there are 2 points here I have highlighted that you can read later, which I have already explained you. So this is friction ellipse concept. So in this friction ellipse concept, you see that I have my driving force, that is Fx, and Fy. So you see that the ellipse has got a major axis O to this point as maximum value of tractive effort possible. That means in absence of Fy, what is the maximum tractive force? In absence of driving or braking, what is the maximum possible? So this is an ellipse. So, but in reality, what would happen? I would not drive corner always only with the pure cornering. So I would also require to apply acceleration or braking. In such scenario, my resultant force is what I should look at for the given slip angle. This is for a given slip angle, this ellipse. One slip angle, this is ellipse. So your reduction of requirement of Fy takes place, and that is what is manifesting to go for another slip angle. So like that, what is that? What you see here? So how do you account analytical formula for that? For a given longitudinal force, what is the lateral force that is at the point of time of a given slip angle can be obtained through this formula. So this formula is a formula for an ellipse. So in this, if you see Fy by Fy4, this is a case study data. Fy4, I'll explain what is this. And Fx by Mmax. So Fx max is what is obtained from experiment. And for a given Fx, what would be my Fy during cornering is what I am going to say. Or for a given Fy during straight motion, side force acting, what would be change in my Fx? So the combination that is in a tire account, I require to understand this friction ellipse concept. So see that how is it done? The first half of this is see here from it is slip angle varying, and I have a cornering force, and this is done for a free rolling condition. So this is done for a free rolling. That means what? There is no traction, there is no braking. So you know the variation of Fy as function of slip angle is plotted. And then for an interesting case study, at slip angle 4 degrees, I would have my corresponding Fy4. So this Fy4 here is F max for that angle, Fy max. And the corresponding tire maximum force is taken as a minor axis, half minor axis, and half major axis and semi minor axis here. And this is one ellipse. So this is how I can have. So here for any given slip angle, what is my Fy in free rolling condition? That's my maximum Fy, and that and my experimental mu value, pure longitudinal force is mu times W. So mu P times W is what is this, and I have my Fy. So there is a compromise. Compromise at any point here. The moment it touches the slip, the resultant goes to the value reaching this mu P times W resultant. That's maximum possible. That manifests or make a tire to increase in its slip angle. So that is what is brought in here. So this equation slip angle, very simple to look at it here. For any value of Fy to get like this, I can have this. So Fy by F max. So Fy by F max. So F max here is Fi4 here, this particular ellipse, plus Fx by Fx max is equal to 1. So this is a simple equation of ellipse and an analytical framework. But it doesn't show explicit appearance of your slip or a skid and slip angle. That's where you have your Fx and Fy comes into picture. So what is this? When you do straight motion and you have a side force, that is being accounted here. So you see here C alpha and alpha, right? When you do cornering and you will have a skid is accounted here. So these two formulas are the derivation with a similar approach what we had in our Julien's model. One can derive this expression. I just have put this expression, final expressions alone, which would take care of the dependency of longitudinal force as function of skid as well as slip angle, or your cornering force as when it is going to be function of skid as well when you are cornering and braking. So both are accounted by this. So if you have this equation and this equation, you see there is W, there is CS and there is C alpha. So and of course the mu road. So operating condition and loading condition of your vehicle is what is going to influence these values. So this is the two expression which would have a combination of this. So if you have done all this with advanced strength of material approach physics, then you would go and look at now the magic formula. I would be able to finish it in 10 minutes this. So you see this formula now, it is having your trigonometric term, all it's a complex formula. So how do you have to read this? Y of x is equal to d sine of whatever is there in this. If you look at that argument, again is C tan inverse of, again there is a bracket, bx minus e into, again it's a bracket. So you see there are three steps going inside. So if you have to evaluate this f of, say, y of x, you have to first go through the innermost bracket calculation, then the outer, then that you have to come outside and then you have to find. There is an example problem of data substitution in the textbook. Please work out yourself so that you would understand how can you substitute data and do it. If you do not do it, I'm sure first attempt everyone would make a mistake. Okay, so there is one formula, what is some number I have put 73, so that it is same number what would you see in your Wong textbook. And the same expression y of x is given now with the capital letter y capital X. Y of capital X is equal to this equation plus s of v. This is called a vertical shift. And this small x is replaced by x plus sh. This is called a horizontal shift. Why this vertical shift and horizontal shift comes in this equation is because in order to account some zero slip and zero camber effect. So those are essentially because of your conicity and ply steer effect of your tire. What are those? I will explain you as I progress in my lecture. And in this you see this f of y represent what? The capital. So when you say magic formula, this is that equation you look at. And in that f of y of x is this. And you have to have what is this SV and SH. This is all how do you put values or what are this D, C, B, E, all I would explain to you now. So these are all called some coefficients, right? These are called a factor. It's called a peak factor, shape factor, curvature factor, E, like that it is named. So what are those factors? What is it depends on? How do you calculate them? All we will see. And this formula is an empirical formula. It's a formula for an experimental data fit. And that data fit such that this formula is obtained so that this f of y can alone represent three parameters. One is it can represent a cornering force, or it can represent a variation of self-aligning torque or a braking effort as function of a slip angle for cornering force and this, and skid for this braking effort. And that is what x is represent. So in this formula, x can be, capital X can be slip angle, then it y would represent either cornering force or self-aligning torque. If x is skid, then it would represent your braking effort. If x is slip, longitudinal slip, then it would represent your tractive effort. So that is that thing. And you see these factors. So as I was telling, the coefficient B in this called stiffness factor, C called the shape factor, D called the peak factor and curvature factor, and you have these two shapes. So let's look at them. What are those? See, look at this is where fit. This is that variation of your capital y of x, a function of capital X, or it is y of x as function of this. I have put both of them. So you can look at there are two sets of axes, small x and small y. So small x and small y, if you take this curve, what is plotted would intersect at its origin. So this is origin. So D is what is the peak factor, the peak value of your braking effort or your side force or self-aligning torque. Peak value is given by this D. What is BCD? It's product of those factors which would give you the tire stiffness. Again, it is a tangent drawn at origin to this curve and its slope, tan inverse of BCD product. Of course, BCD depends upon its loading and operating condition. We'll see in a while how these are quantified. But now if you look at this product tan inverse would give you this slope, and that slope is what is your longitudinal slip or skid stiffness of the tire or cornering stiffness of the tire and so on according to the value of x what you substitute. And you see now this SV is what is vertical shift. So vertical shift is what you can see that I have a capital X axis. I have this capital X axis which is added, which is parallel to this by this vertical shift. That's what is vertical shift. I have similarly a horizontal shift to have my capital Y axis. Why is it? Because with respect to small x, small y axis set, this curve is not symmetry. In order to account this unsymmetric nature, also this Ply's and the unsymmetric nature is because of Ply Steer and Conicity effect of your tire. They, what are those? I'll explain you. And that to account, you got your axis shifted by SH and SV, right? Those data will be provided by the formula copyright owner. Those people are Hans Fajeka and their team, right? And Professor Hans Fajeka is from Delft University. They are the legends of defining this variation of forces in the contact of the tire road interaction, and their models are very popular in almost all any vehicle dynamic simulation software. If you take these tire model were used to model your tire for your vehicle dynamics analysis. Okay, so continuing with that, you see now I have put a plot for XY alone separately and X and Y so that you would clearly see this shift, right? So what are these values here? You have to see is what is given here. See the I'll just read out this. For a given values of coefficient, the curve shows an antisymmetric shape. That's what I was explaining you with respect to origin, x is equal to y is equal to 0. With respect to it's not a symmetry; it's an antisymmetric nature. That's why you are given the shift. That's what is explained here. And let's march ahead. Looking at what is this conicity and Ply Steer. So conicity and Ply Steer are tire forces which have received an added attention of increasing radial tire usage. So radial tires are responsible for this attention of conicity and Ply Steer. As the tire rotates under load, forces are generated transfers to the direction of rotation of the tire road interface. So tire rotates on a vehicle constrained to fix in the axle is different, right? But the tire, you take a free tire and just roll that on a floor, you see that won't go in a straight, it will go automatically take a turn. That is the reason why, that's because of the reason called the conicity effect of your tire. So we'll understand that. So these are called, the forces due to this is called conicity and Ply Steer is residual tire forces. They are called the residual tire forces, and they are influenced by tire design and construction features of the tire, as well as the direction of rotation. So direction of rotation from conicity, it is no matter. You see, a cone is rotating about its apex like that. So the force is always towards the apex. Whether it is rotating clockwise or counterclockwise, the direction does not change. Whereas Ply Steer effect is a steer effect in your tire because of the orientation of the cards that you have seen in plies. And the outermost ply card orientation is responsible for changing it. So the tire rotates in one direction, the force direction is one. If it changes reverse, and then the force also will change. And these forces are the residual forces in a tire. Before you fit in your vehicle, or if you have a tire it's assembled in a rim, before it is put in your vehicle, if you are rolling the tire, it won't go in straight. That is, it will have some turning or rotating effect that is coming from this, and that is what is the residual forces default present in your tire wheel assembly, and that is to account is what is this horizontal vertical shift has come. So let's look at in particular what is this conicity and Ply Steer. So this term conicity was apparently derived by considering tire to be tire to assume the shape of truncated cone. That's what. If you look at the truncated cone, this is going to rotate either clockwise when you view from here or counterclockwise. It would generate the force towards this apex. Something like you look at your camber, the cambered tire, camber angle is the wheel plane angle to the vertical plane, XZ plane is what is camber angle we define, and the camber thrust is generated. So something similar to that here. Since you have the side force given by that, this is called pseudo camber. It's called a pseudo camber. So that is because of the conicity effect. So the tire is turning when you are freely rotating tire wheel, not going in straight line. It's because of there is an inherent nature of this conicity effect, right? And what is this Ply Steer effect? Is you see this picture with the tire with the orientation of the cards like this on a outermost ply. So you would see that this ply would create a steering force like a steer effect. That's why it is called Ply Steer effect. So the and why that would create a slipping of your tire. Right. So Ply Steer, the term was apparently derived from reference to the influence of plies in the tire in generating forces, which could steer a vehicle from its intended straight line course. So it is intended to go in a straight line course, but it is going to create some side force. And that side force direction would change. If you see from here in this rotation, this is the side force. If that rotation reverse, the side force, this will change. Right? The force were theorized to be related to the direction of cards in the outermost ply. That's what is seen in this diagram, right? So thus Ply Steer by definition is a force component which changes direction with the reverse rotation when measuring tire lateral residual forces. Similar forces would be generated in reversing the tire operating at a small slip angle, So when you have a small slip angle, you have this, and that is why this Ply Steer force is also referred as with the word slip, pseudo slip. So it is similar to slip angle. Slip angle generated, you have a side force. So the slip angle generation is because of the outermost ply cord orientation. When it is not actually subjected to a tractive force, that means driving torque or braking torque when you take. That's why it's called a zero slip. So these two effects are to be accounted. That is the reason why in your magic formula model, you see that there is the shift SV and SH. And I think now you understood this formula and this curve. So at the moment, this does not account combined cornering and braking. If you look at this equation 74, that is y of capital X equals this, and where X is given by this, is only representing at a time your cornering force is slip angle, or self-aligning torque is slip angle, or braking effort a skid. It is not a combined effect brought in there. So to bring in this combined effect, there is an additional factor called the G factor, which is not in this equation. I would say at the end of my lecture, what is that, right? So let's proceed further. Now it's very simple. I'm not going to explain much. Rather, I would say how are these coefficients are determined for this particular case of magic formula consideration. So look at that. This formula could help you now to plot this variation in your loads. Variation in your loads. Variation in your load. So, if, for example, you look at this 1.44, that brings in your side force as function of slip angle. As the load increases, you see they are changing. So, this is that fit according to this magic formula. And you see here the self-aligning torque. Self-aligning torque is increases and then it is again decreases. So after this, it's decreasing is because your pneumatic trail is going to be zero at that particular slip angle. So you should have a slip angle so that you would be able to have an advantage of arriving at the maximum values of self-aligning torque as well. And if you look at the same magic formula as a function of skid, if you plot, and you would vary your load, and then you can get such kind of thing. So the same formula for different loads, we are able to get this, means that formula is best fit of your experimental data. So that is what you understand from this. So these are some case studies, the data for the formula what we have been looking at now. And the values of these coefficients also available in this table 1.6 in the textbook for a car tire. So you see here it is Fy, side force, self-aligning torque, and in this case it is only braking effort. And you see the skid value to be considered percentage minus in the formula. And slip angle should be put in degrees. So this is very important. You can't put in radians then, right? This should be put in degrees. So you are given all these values of B, C, D, all. These all values are obtained with the curve fit technique of experimental data. How this is obtained is not our worry. Our worry is any commercial software using this Hans-Pajeka model, it will have n number of coefficients. So this is the base model of Hans-Pajeka model, magic formula. And it is limited, it doesn't account combined effect, what we have seen in our Julian's theory model that I have explained you in a while back. That doesn't brought in here. So this model, this tire model, if you have, this model will come with all this table data, coefficient data, all. So when this model is integrated in your vehicle's dynamic model with the computer simulation application, it would appropriately choose the scenario and work on that. That's what you should keep in mind. So this gives you all this factors here. This is stiffness factor, shape factor, peak factor, curvature factor, your horizontal shift and vertical shift, and the product of BCD. So tan inverse of product of BCD would give you what is your cornering stiffness or what is your skid stiffness and so on that we have seen. So this table go with the formula. So if you have the formula, means understood the formula, means you should also look for this data and it is available. And how these coefficients are coming, they are a function of normal load and camber angle of the tire. So that's what you can see. This peak factor is coming out with this variation. See, it's a quadratic variation of your normal force on the tire. But this, what is this A1 and A2? These coefficients are going to be given. I will give you now that, show you that values. Where this FZ is kilonewton. So this unit should be strictly followed. So this is that peak factor expression, which is function of your normal load. And then cornering stiffness, you see, it is again to get BCD. So you require these coefficients additionally come. You see the trigonometric term comes here, and it's also function of your FZ. And you have now so for 5 coefficients. And self-aligning torque again is function of FZ, and again you have coefficients A3 and A4 to be used here. So these are the formulas and the dependency on normal load. And you see now, shape factor, it is almost independent of FZ. That's what they propose. So this independent of FZ. So you have your constant value proposed. So C value factor is this. If we are you are using equation for this, you have to take C values. If you are using equation for aligning torque as slip angle, you have to use this. Braking effort at skid, you have to use this value. That is C. So you have a C, D, B. So I would be able to have my B. And the curvature factor depends on FZ. All are represented as nonlinear variation, and it's function of some coefficients also there. And there are 8 coefficients so far, and those coefficients also are provided here for you. So if you have to calculate your lateral force or self-aligning torque or braking effort, you have to choose these values there. So this is the tire model data for a particular tire of the car tire. Like that, you would have for every tire coming out with this coefficients. So every batch of tire, whether it is for passenger car or truck tires, they will undergo numerous experiments, and they would be coming with this kind of coefficient. So this is one of the base model. Today's coefficients reached beyond hundreds. So you see that how complex this curve fit. Why it's reached beyond hundreds? Because it has to be a formula to account real-time scenario. I drive my car, do hard cornering, I also apply braking. It has to account. But the model what we are looking at now does not account cornering come braking or cornering come traction. It's only pure cornering or pure braking only is considered here, right? So these values of coefficient additionally you have from A9 to A13. So you may ask why do we require these? That's what I will explain. There is a dependency of these factors on camber angle as well. So you will see that here. So the shift, that's what you have seen. Conicity Ply Steer is pseudo camber or pseudo slip that you have seen. So the pseudo camber effect is account. You have this delta SH, which is required this coefficient, which is given in the table, and vertical shift is accounted like this. So change in stiffness factor delta B is given by this. So you can just go through this all. So if you are having your table data of coefficients, you would be able to account your pseudo camber, pseudo slip by horizontal vertical shifts, and you would also have your normal load variation and effect by means of different factors that are appearing in the magic formula. And this note is something I was telling that this model does not include combined effect of slip angle and skid. So if you have to account, you require an empirical weighting function called the G that has been introduced here. So again, if you look at to define G, I have D dash, C dash, B dash. This prime is put here dash is to differentiate this from the values that are there from magic formula. We also see that BCD. Here it is D dash, E dash, B dash, and they are here to account empirical constant. Those values also will be given along with this model. So this is important to note, and we are about to finish it. That it should also be noted that the discussion so far what we had is only for steady state cornering behavior of tire. That is what. So it will be, if I use this formula with this coefficients and the factors, I would not be able to convey my variation of or cornering force and braking force together, like one frictional ellipse concept that we have seen. We looked at just a magic formula model, which is a base model, but that model could be extended, understood further if you are going for these references given in your textbook. So if you read that, you will have more and more interesting aspects. So I see there are students in your projects that you are working on tire models, especially those competitive students. There is a team working on tire models. So they always worry, what is tire model? How do I get this? So this is commercially available, but you need to understand what are these coefficients, when they are to be appropriately used. How to use this model is what is learning. Like you do understanding of your design of machinery elements or design of transmission system and so on. You have studied those courses, so you know you are strong in strength of material, but that is not sufficient. There are a lot of lookup table and you have got a data standards. So you have to understand how do you apply those standards while designing. Something similar here. It is that as a user of your vehicle dynamic engineer, you should be more worried about how do you understand the given formula and the associated coefficients and table. How are those coefficients and table are derived is not a matter for you as an application engineer. But as a researcher something, you should see how that is all going. So for that, you have a volume of textbook given by Hans Pajeka, by Tire Dynamics textbook itself. And that itself is a different course, advanced course, may not be possible at an undergraduate level to study, right? There's no scope in that. It's a very special courses, those are all. So as you perceive that, you would do it. But when you are to study that, you would not feel any difficulty. You should feel as ease of going through those textbook, because you have done some base course like vehicle dynamics course. You are exposed to that kind of complexity. So whatever that I have been discussing today's class may not be much for your examination point of view, but you should know what is that is happening in industry, how we should go and look at them. That's what is the primary objective. So with that note and additional references from 26 to 30 for tire models, enhanced tire models to study, I would recommend and stop today's class for tire dynamics. And as a whole, we are completed with our course vehicle dynamics course. So with that note, let me finish today's class. And there are 6 students now. The others would have left. They can join and see this. I would put the necessary instruction related to your assessment, maybe the schedules that you have to follow for your final review. You can go through and then we will accordingly act maybe tomorrow. And tomorrow I'll try to complete your final review. That would be completing our course, even assessment point of view, internal assessment point of view. And before comprehending, I just want to say that another minute, in a minute, what we have seen in our course. So we have started our course, vehicle dynamics course, understanding some mechanical vibration basics, wherein we looked at free vibration, forced vibration. We started our study with simple harmonic motion, looked at free vibration, forced vibration, then the response for the harmonic excitation. We have looked at what is steady state response, what is transient response, and then what do you mean by magnification factor, and so on. So these are all some fundamentals that we have looked at in our mechanical vibration course, module 1. And then we started our vehicle dynamics course with the vertical dynamics first, and then we marched through lateral dynamics, then we finished longitudinal dynamics. Finally, we were into tire mechanics, and today we have completed that. So there are 45 lectures altogether that's available online today. That's a treasure, according to me, for this course is made. Would help any student, not only for undergraduate level, also for PG level. In fact, those lectures would be beneficial for practitioner or engineers working in an industry. They want to have a ready reference learning. The course which I have planned and systematically taught and recorded would certainly stand in upper hand. And really, at this juncture, I would take my I would put forward my sincere thanks, my sincerity and attitude to my Professor R. Krishna Kumar, because of whom I have learned this course. Under his able guidance, I was able to come out with my PhD work in the field of tire road interaction, noise, automotive NVH, and general perspective. So I really thank my professor at this juncture, and I conclude my class. So all the very best for all of you for your final assessment exam, and we will plan our final review for your DA tomorrow. I will upload the schedule for the same. With that note, I would like to conclude today's class. Thank you so much for attending. So I'll stop sharing,
Yes, sir.
stop recording.